many parts of the world, people involved in wood preservation research need to use field tests to assess the effectiveness of new wood preservatives or to determine the susceptibility of timbers to biodegradation. Here in Australia, CSIRO Division of Chemical and Wood Technology has many such field test sites for this purpose, and we will find that most of them represent vastly different conditions of climate and hazard. We're now at a site near Melbourne where our mycologists John Thornton and Gary Johnson are inspecting field test stakes and rating them for the amount of decay present.
Decay rating 1.5. Brown rot.
Elsewhere, our field tests represent a high tropical decay hazard to stakes, so that their comparative natural durability can be determined. At some of those sites, the hazard from termite attack is very real. In Australia, termites represent a major hazard to timber in service, and we find it is often necessary to include a termite hazard in a field test site so that we can assess the efficacy of our new wood preservatives or the natural durability of timbers to all the hazards to which they would normally be subjected in service. Research studies in the laboratory have been conducted in many countries for many years. More recently, the concept of the so-called fungal cellar has been used to expose small timber specimens to a simultaneous decay hazard. The term fungal cellar originated in Europe, where these experiments were conducted in cool, moist basement areas, particularly at the Bundesanstalt für Materialprüfung in Berlin. The technique was taken up and adopted elsewhere in Europe, and also at the Forest Research Institute of New Zealand in Rotorua, and of course at CSIRO in Australia. In Australia, CSIRO mycologists John Thornton and Gary Johnson used mixed populations of fungi, bacteria and actinomycetes to conduct accelerated studies of the natural durability of the heartwood of a range of Australian and exotic timbers to decay. In 1982, they, along with Dr. Harry Greaves, proposed that the term Accelerated Fields Simulator, or AFS for short, was more appropriate than the term fungal cellar for describing the use of controlled environment chambers in which biodeterioration research and testing is conducted against soil fauna as well as against fungi. Following the success of their fungal investigations in the AFS, Dr. Thornton wondered whether it would be possible to extend the versatility of the AFS concept to include a hazard from termite attack and thus attain realism with the field situation. So the mycologists called upon the expertise of the entomologists. Jim Crefeld, Peter Burridge and I enlisted help and advice from our friends and colleagues Tony Watson, Bob Barrett, Lee Miller and Michael Lentz of the termite section at CSIRO Division of Entomology in Canberra. Cooperatively, we collected an entire mound colony of Coptotermes lacteus in Canberra and transported it back to Melbourne for incorporation into an expanded concept of the Accelerated Field Simulator. This is how it was done. First of all, we went into the bush and selected a freestanding mound such as we would normally choose as a source of termites for our laboratory bioassays. Jim Crefeld and Bob Barrett, using picks, break off the hard clay outer casing to reveal the internal nest structure of so-called carton or woody nest material in which the population of the colony may be found. When collecting termites from mound colonies like this in the bush, it is important to prevent the termites from escaping into their network of galleries and tunnels in the soil and surrounding areas beneath the nest. It is therefore necessary to trench around the colony and to undercut the mound so that escape routes are terminated. Once this has been done efficiently, the entire mound colony structure may, with appropriate expertise and equipment, be winched out of the ground and onto a trailer for transportation to the laboratory. It isn't always easy or straightforward, but it can be done. Before the team leaves the bush, they make sure that the crater that was once a mound structure is filled in so that it does not become a trap for livestock or wildlife. And we leave the area much as we found it, minus the termite colony. Back at the laboratory in Canberra, the inner section of the mound is loaded into a specially prepared galvanised bin that will be its new home for a long, long time. At the bottom of the bin we have placed sand with some nice, juicy, susceptible timber as a food source for our termites that have, so rudely, been removed from their natural habitat. Just to make them feel at home, the soil around them in the bin is supplied from the area where we found the mound. Afterwards, the whole thing is transported 800 kilometres by road to Melbourne. And how did we make them feel at home when we got there? First of all, Jim Creffield had a great idea. Why not pulverise the outer casing that we'd taken off in Canberra, mix it with water into a slurry and then plaster it over the surface of the mound? We did this and it worked. The termites in the mound sealed any cracks that appeared in their new external coating and thus set about making house in Melbourne. Now, the environment in the Melbourne AFS at CSIRO was a bit different from the bush near Canberra. For a start, the AFS runs at 28 degrees Celsius and 90% relative humidity. Furthermore, it is mostly in the dark, and the bottom of the mound is not only not close to the water table, but it's not even in touch with the ground. So, how can our termites control their environment? Interestingly, they responded in a way that was completely alien to Australian termites. They controlled their microclimatic conditions within the mound colony by building quite uncharacteristic structures out from the mound to permit some appropriate acclimation with the conditions in which they found themselves. While they were feeding on the wood that had been placed in the bin under the mound, they continued to extend these rather ethereal construction techniques. However, when the real test started and they were put to work, they partly changed their response. After several weeks in the AFS, the bin in which the termite mound was confined was connected by a system of PVC pipes to either of two exposure tanks containing 5 replicate stakes of 70 timbers, including a copper chrome arsenic treatment as a yardstick. One tank contained specimens that had been subjected to a 20-week pre-decay hazard, and the other tank contained replicate specimens subjected only to moist soil for 2 weeks. The termites were able to enter either tank at various points or to go directly to a feeder box containing untreated susceptible timber as a food source. Almost as soon as the tanks were connected, our termites began to behave as we would expect them to do so in more natural situations. As well as building the grotesque superstructures, they simply surface plastered their mound as is normally done in the field. Thus the mound was able to grow in size. In the tanks, test specimens were visited and assessed by the termites and, depending on the species of timber or the preservative treatment, were either attacked, ignored, plastered over, or, in the case of highly resistant species such as teak, covered with a barrier that was obviously designed to protect the termites from obnoxious and repellent materials. So John Thornton's basic idea had worked, and had been seen to work. It was possible to provide 2 hazards in the laboratory to simulate those same two hazards that are found so often in the field. In this assessment, inspections are carried out at every 4 weeks, and the specimens are rated according to their condition. The biodeuteriogen is determined, and scores are allocated for both decay and termite attack. The whole technique has extended the scope of laboratory assessments and produced some rational determination of durability according to both the decay and termite hazard that is so often present in the field.